4.6, the log-normal distribution. And this video has the following objectives: to define the log-normal distribution and to calculate the probability of outcomes using the log-normal distribution. Some of the examples of log-normal distributions are the milk production by cows. A cow, after calving, has a peak production in about 40 to 60 days, so this is about in between the first and the second month, something over there. So it has a peak production, and then after it steadily dropped the production until about the 10th month. So we can see the distribution is skewed. It's larger at the beginning and steadily decrease at the end. Second example, we have the lives of industrial units with failure modes that are characterized by fatigue stress. So we expect the life to be something like that. So this is like the mean life we expect it to be at one point, and after that it will still work, but the probability that it works for a long period is much less. Another example is the amount of rainfall, like for example telling the probability of a rainfall in a day. So we can have that even in days like today that the probability was like the 10%, it still happens, so we still have rain even though that the probability was the 10%. The size distribution of rainfall droplets, or we can say for example hail, the size distribution of hail. So a small hail, so this is the size. Small hail will have much more probability, but we can still have some probability of getting large hail. And the volume of gas in a petroleum reserve. So initially we have a lot of production and then the production will decline. So the interesting thing about the log-normal distribution is that it's skewed, and in a lot of situations the important part that we want to take into account are the tails probabilities. Okay. So what's the main characteristics of a log-normal distribution? Well, we can look in the tail. So basically we have outliers, and that makes that the distribution is skewed. So it's like having so in these cases the normal distribution is not really appropriate because the normal distribution is symmetric. However, the log-normal distribution is related to the normal distribution, and and in fact we use the normal distribution to compute the probabilities. So for example, if we have our normal distribution that has some mean and some standard deviation, so we can say that this is normal distributed, so X is normal distributed with mean mu and variance sigma square. Now, if we operate the variable X and we say that Y is equal to the exponential of X, so e to the X, so what we are going to have is a distribution that is skewed. Okay, and in this case we say that this is log-normal distributed with mean mu, and with, I wouldn't say mean because it's not the mean of the log-normal, what are the parameters that we use to create the distribution. So we say with parameters mu and sigma square. Now we can move actually in the opposite direction. So if we start with some variable which is log normal distribution, so we say that if y is distributed as log normal, so log n with parameters mu and sigma square, then x equal to natural log of y is normally distributed with parameters mu and sigma. The parameters are the same. So when we operate a distribution that is log normally distributed by calculating the natural log and then we plot it, we are going to have a normal distribution. So we are going to use that fact to compute the probabilities of a log normal distributed variable. So how is the relationship with the normal distribution? Well, first of all, we keep the mean and the variance of the normal distribution, and we're going to use the same equation except by some part, this one that is in red. So instead of input the variable, we input the natural log of the variable. If we do that, then we are going to have a distribution that is log normally distributed. Now, there are some basic things about our new distribution. First of all, because we are applying the natural log, so natural log is only defined for positive numbers. So x is only defined for positive numbers, and for x less than or equal to 0 is not defined. So we say that the probability is equal to 0. Now, we said that y is log normally distributed with parameters mu and sigma, and we can prove by applying the definition of mean and variance that the expected value of y, that's the mean of y, is given by this expression, this exponential expression, e to the mu plus sigma square over 2, and the variance of y is given by this expression, which is the sum of two exponential functions. Now, in general, we are usually interested in the right tile where large events occur and can cause a lot of destruction or economical damage. So meaning this part, like for example, the probability of large flooding, it happens rarely but happen. So, or the probability of a large earthquake or a hurricane. Okay. Second things, take into account, even though that the parameters of the log normal are mu and sigma, we are not saying that this is the mean and this is the standard deviation of the log normal distribution. Those are given by these expressions. However, we constructed with mu and sigma of the normal distribution because we are basically using the same function. Okay. By the way, in the book there is an error in this equation. It's equation 430, so it has an extra x or something like that, so be careful. Now, how do we identify that we have a log normal distribution? Well, basically what we have to do is we take our data, and after taking our data we plot it, and we can see that the distribution is like that. So let me mark it for good. So this is something like that. So we can realize that it's skewed, that the tail is on the right. And if we apply the logarithm to this data, so if we do, so this is this, we are going to call it y. And if we apply the natural log of y, and we call this x, and then we plot, we are going to have something that is normally distributed. Okay, so that's the way that we can tell that our distribution is log normally distributed. So we take our data, we plot it. Okay, we have a tail to the right, it's positive, and then we apply the natural log to our variable, and we can see if there is a bell shape in the new distribution. So then we can say, well, this is log normal. Okay. In practical terms, so what we have to do to compute probabilities is we are going to use the actual normal distribution and the normal tables. And so remember, we have our data is in, we are going to call it now in the variable y, and we are going to transform it into x, and the way of doing is that x is equal to the natural log of y. Okay, so then here we compute mu and we compute sigma, the standard deviation, and with those variables, so we take sigma and mu, we feed our log normal distribution. So then after, let me go over here, so we compute the mean of y and the variance of y, okay, using these equations. Now we are going to jump into the Desmos application to illustrate the log normal parameters. We are now inside the Desmos application following the link provided in the notes. I initially have the normal distribution function, which is given by this exponential, where S and M mean S is sigma, the standard deviation, and M is the mean. So I have these two parameters freely, so I can move the standard deviation, large standard deviation, smaller standard deviation, the mean, so we can move the mean left or right. And now let me do the big change to transform this into a log normal distribution. Basically the change is to change x by the natural log of x. So now we can see that the shape of the curve is not symmetrical, it's skewed to the right, and the mean also of the standard deviation is no longer the mean of our distribution. One thing that I define here beforehand is that x is only valid for positive numbers. Okay. There is another way to produce our log normal distribution, and it's done in two steps, and it's usually what we do when we have the data. So we have an additional variable r, and we apply the natural log to that variable, and then we use the standard, the normal distribution to plot it. Let me plot it in this point, and we can see that the blue, which is then our new plot doing these two steps, is exactly the same as the initial function. So this is usually what we do when we are working with data. So we apply the natural log and then we work with the normal distribution. Now, what I'm plotting here by x equal m is the mean of the normal distribution. But the normal distribution of the log normal distribution is given by a different expression, is the e to the m plus s squared over 2. So that's the mean of y, what we call the mean of y in the book. And I'm plotting here the mean of y. Let me show you. So we can see the line in black is the mean of our log normal distribution. It's much more clearly the mean that the sigma parameter in our log normal. So still the log normal is written in terms of sigma and mu of the normal distribution, but that not represent the mean of the log normal. The mean of the log normal is given by this expression. Also, the standard deviation is given by this expression, the square root of the exponential, or e to the 2m plus 2 s squared minus the exponential of 2m plus s squared. And I'm plotting these 2 points here to see. So I'm plotting m minus y and m plus y. So we can see these 2 points are defining the mu minus the variance, minus the standard deviation, and mu plus the standard deviation. So if we move the parameters of our distribution, they will change accordingly. So a big S, it will represent also a big S in our log normal. And the change of the mean in the normal distribution, it will change also the mean in our log normal distribution.